Record this session? Yes, I have started the recording and we'll upload the recording on YouTube, right? Because I think that's a good platform. Uh, it's going to be slow. Yes, sorry? No, no, three, four, five. Yeah, five also. Again, the questions are going to be pretty easy, right? They will be mostly based on what we are going to discuss, right? Some simple problems. But other than that, it won't be much problems, right? And there is no model paper given by the university as of now. So that is a little slight issue there, because usually the university gives us model papers, so that becomes based on that usually students study. But this time there is no model paper, but we do have some previous year papers. There is a question bank maybe that has been shared with you or not. We'll look into it, right? Yeah. That I won't tell you. Sorry for that. Uh, but yeah. So, but we are working on the question paper. The work is going on. Yeah. All right. So there has been a message sent in the chat. Can you share important questions for second internal? Well, again, if you do not have the question bank, please let me know. Right? There has to be a question bank. I do not have access to the question bank yet. But I think Professor Shavana might be having the question bank, so she will be giving you the question bank. Okay. So we'll wait for 1 more minute here. Uh, no one else is joining right now, correct? Okay. Let's check whether everyone is awake or not. Yes. So can we all show our thumbs ups or any other emojis? Fantastic, fantastic. Whoa, this looks amazing. Yeah. Okay. So we will start. Bharat has raised the hand. Okay, raise hand is basically okay. You want to show your thumbs up? Maybe that's right. Hmm. Bharat will be talking with me. Okay, you are talking, so let's keep it that way. Not a problem. Okay, so let's start. Right. This module is extremely easy. All right. This module is very easy. Graph coloring and some applications of that in the four color problem and the five color problems. And then there is a greedy coloring algorithm. The greedy coloring algorithm is, it's a small heuristic algorithm for coloring the vertices of a graph. The five color theorem uh, and the four color theorem is, these are like kind of theorems in which we say that a graph which can be drawn on a plain sheet of paper, a planar graph, can be colored with three, four, or five colors, right? As of now, in the beginning, everything would look very confusing, here very confusing, but once I start writing, everything will be easy to understand. Um, and there is this topic called matchings and coverings. right? So the vertex cover and the edge cover, these are two very interesting concepts, right? And in which in the vertex cover, is a set of vertices in which, such that all the edges in the graph has at least one of the chosen vertices, and the edge cover is similar to that, in which it's a set of edges in which every vertex is covered, right? And then there is a matching. In there are basically two types of matching that we will maybe go ahead and read. One is maximum matching, another is perfect matching. The chromatic polynomial is a little complicated topic. Maybe we can skip it for now, or maybe at the end, if everyone is awake, we can go ahead and try to find out. Otherwise, chromatic polynomial, isomorphism, and one or two more topics we can, cover tomorrow in the next lecture. And we'll start with the chromatic number and what it means by coloring a graph, right? Okay. So let's start here. I would start by drawing a simple graph over here. This is a vertex which is colored in blue, right? Okay. What I'll do is I'll change this page, right? This page background to maybe plain. Yeah, this is better. So this is a vertex, and there's an edge which is going to another vertex, right? Then there is another edge which goes to another vertex, and there is another edge which goes to another vertex. So this is the simplest of all graphs, right? So in this graph, we have got four vertices and four edges, right? Four vertices and four edges. Now, we will be doing an experiment. What is the experiment? The experiment is as follows. First, let me redraw this vertex over here. Let me redraw this vertex here. Yeah, and this vertex as well. Let me just draw circles here. Okay. The experiment is we want to color the vertices, right? So, for example, I am coloring this vertex as a red vertex, correct? Now, I want to color the next vertex, which is over here, right? This is the vertex 1, this is the vertex 2, this is vertex 3, this is vertex 4, right? So the vertices are 1, 2, and 3, 4. I want to color 2, the adjacent vertex, with a different color. So 2, let's color with green, right? Okay. And we would want to color the third vertex. Sorry, someone was talking. My voice is breaking. Okay. What I'll do is I will put on my earphones. I'm not audible. I'm not audible. Am I audible now? Am I audible now? No? Still not audible? Voice not not visible. I don't think not visible is a problem. What about now? Is it fine? Better now? Little bit okay. Now better. Yeah, yeah, yeah. Uh, okay. I think yeah. Anyways, okay. So let's continue. Right? Let's continue. It's fine. Correct? Okay. So now till now what we did is that we colored the vertex one with red. We colored the vertex two with green. So the challenge here is we want to color the vertices, right? We want to color the adjacent vertices different color, right? We want different colors in adjacent vertices. What is an adjacent vertex? 1 and 2 are adjacent vertices, 1 and 4 are adjacent vertices, and so on, right? So these adjacent vertices would be of different color. So you can see that Um, the vertex 1 is red, the vertex 2 is green, the vertex 3 is like, let's say it's magenta, right? And vertex 4 is orange. Now, can we decrease the, how many total colors have we used? We have used, we have used a total of 4 colors. Yeah. But can we reduce the number of colors here? Is it possible to reduce the number of colors? Let's see. Can we reduce the number of colors? Let's get the graph again, right? Can we reduce the number of colors? Because we don't have so many colors. Let's say, there are like 620 vertices. Getting 620 colors is very difficult. So let's start with vertex 1 with one particular color. And what we do is that with the second color, we will color all the adjacent vertices of 1, right? And then we'll repeat the first color again. So you see here, what did we do? We colored red, we colored the vertex 1 and 3 are colored with red, and the vertices 2 and 4 are colored with green. So what are the total number of colors that have been used to color these particular vertices? It's 2. The total number of colors is 2, right? So we have used 2 colors only, and this is the minimum number of colors that we have to use, and therefore the chromatic number of this graph, let's name this graph as G of G, is 2. Now the chromatic number is represented by this symbol. This symbol is called chi, chi, right? Chi of G is equal to 2. So the chromatic number of this graph G is equal to 2. This is important, right? So maybe in the tests, we will be giving you a graph, and we'll be asking you to find out what is the chromatic number of that particular graph. What we'll do is we will like, let's take an example of another graph. uh, let's say the graph is looks like this. So again, let there be 4 vertices, right? Let there be 4 vertices, and instead of these being the edges, let's introduce another edge. So this is another graph G, in which the number of vertices is equal to 4, the number of edges is equal to 5. Correct? Okay. Now let's start coloring. Yeah, so of course, we'll name these vertices as 1, 2, 3, and 4. Let's color the vertex 1 with red. Now, the adjacent vertex of 1 is 2. Let's color this vertex 2 with blue. Now, since we have colored the vertex 2 using blue, we cannot color the vertex 4 with blue, and we cannot color the vertex 4 using red as well. So we have to introduce another color here, and we have to color the vertex 4 with the third color. Now, the vertex 3, we can repeat the red color over here. Correct? So, in a nutshell, the vertex 1 and 3 are colored with green, right? The vertex 2 is colored with blue, and the vertex 4 is colored with orange. And once we have this coloring, yeah, because 3 is not connected with 1. The vertex 1 is red, but we cannot color 2 and 4 with red because 2 and 4 are adjacent to 1. But on the other hand, 3 is not adjacent to 1. So in the 3, we can repeat the same color. Look at the previous example. In the previous example, 2 and 4 are not connected. Hence, we could color them with the same color. Right? Look at the definition here. Color the adjacent vertices different. The adjacent vertices should be different. Look at the left side box. That is the definition. That is the rule. Correct? So the chromatic number chi of this graph G is equal to 3. So we need 3 colors to color all the vertices of our given graph. Okay, so this is the chromatic number. Okay, now before we move on, right, let's look at one definition. The definition is that of a planar graph. Definition. The definition is that of a planar graph. Planar graph. So planar graph is a graph that can be drawn on a plane surface without any intersection of edges. We don't want the edges to intersect. All right, everything is fine. We don't want the edges to intersect. No two edges should be intersecting. Let's look at an example of the same. Look at this graph over here, this triangle graph, right? This graph is a planar graph, no issue. Let's look at another graph, this square over here. This is a planar graph, not a problem. If we introduce an edge between the opposite vertex here, this is also a planar graph, right? Okay, now I am going to add another edge to this particular graph. Okay, now this edge will be between, let me color them, between the top left vertex and the top right vertex, right? Now I can draw this edge by circling around. This is allowed, and hence this is also a planar graph. All right, so these are all planar graphs that we have drawn. Okay, a counter example of the planar graph would be, let's see, let's draw, a pentagon, and we have an edge here, we have an edge here, and we have another edge here. Now I want to draw an edge between the red on the top and the red at the bottom. However I try, I will have an intersection. If I try this way, right, let me try to zoom in here, right, so it will be even more visible. Look at this on the right side of your screen, rightmost corner of your screen. You will be seeing that there is a new edge, red edge, that we have tried to build. But this edge is not a valid edge because there is an intersection which is going on here. Okay, let's try to draw it straight here. Still, it is an illegal edge because there is an intersection happening here. Okay, let's try to draw it this way. There are two intersections happening. It's still illegal. If we want to draw an edge like this, there is one intersection here, so it is illegal, right? So this particular graph is not a planar graph. Now, why is this important? Now, why is this important? This is important to understand the 4-color problem and the 5-color problem. Okay? Because see, if we are trying to draw this graph on a 3-dimensional structure, the rightmost graph, then we can easily draw this. Just imagine that this red edge that we have drawn is hanging in the air, right? So it is not intersecting with anything else. On the ground, I have drawn all the black edges, and the red edge is a kind of a wire hanging in the air. So there is another dimension that is added. It is no longer on the plane. It's no longer just on the floor. Now I am taking the room also in consideration, right? So the dimension here increases by, and we are not being able to understand that. Therefore, we are not being able to draw this particular graph in on the plane, on a two-dimensional plane. Okay, so this is not a planar graph. The definition of the planar graph, just to have a revision of the concept, is a graph that cannot be drawn on a plane surface without any intersection of edges, right? There should not be intersection of any edges whatsoever. Okay, now now we'll go into the next subtopic that we would want to consider, we'd want to cover here in today's lecture. That is the four color problem. So the four color problem states the following, right? So let's write down the statement of the four color problem. So the four color problem states that any planar graph, any planar graph can be colored using, very important words coming up, at most four colors, such that no two adjacent edges, no, not edges, sorry, vertices have the same color. All right. So, I mean, the proof of this is, it's a little difficult to do, to be honest. But like around let's say 50 years back, this particular theorem was being proved. This is a theorem basically. I've written a problem here, but this is actually a theorem. So this theorem was proved using certain computer-aided methods. Uh, Maybe in a later semester we can have a small talk on this. So the four color theorem is very important because like it says that if you draw a map, right? Like if you draw a graph on a piece of paper on the plane, right? You are not, like folding the paper or, like sticking another piece of paper. You are not making it three-dimensional on a two-dimensional plane. If you are drawing a graph, then at most four colors are required. Like it could be two colors, it could be three colors, or whatever, but only maximum of four colors would be required to like color the graph such that two adjacent vertices do not have the same color. um, what I'll do is that I'll go through the five color theorem as well. It is very similar to the four color theorem. And then we'll come and look into a few examples of these two theorems, right? I think that makes sense. So the five color theorem is also the same. The five color theorem, five color, five color theorem or problem. I'm writing problem here. The theorem is at the backdrop. The five color problem. It's a theorem, but let's highlight this particular statement as a problem. So again, any planar graph can be colored. So this is kind of a like how do I say? This is kind of a easier version of the four color problem, right? We have relaxed using one more color. So this can be colored using at most five colors, such that adjacent vertices are colored differently. Just a minute. Colored different, right? Okay. Now, um, yeah. So let's look into an example, right? So if we look into an example, maybe things will be a little bit more clear, right? So let's consider a map, maybe, countries, because if you have, if you remember when we were kids, or maybe, while looking into maps of countries, we usually represent countries by different colors, right? We draw the outline of the countries, which might look like this, right? This is one country, that is, then there is another country like this, then there is another country like this, they are sharing borders, right? There are three countries here, four countries. There is another country. Then there is yet another country. So there are like good number of countries here and there, right? So what is the minimum number of colors we need to color this map? So that's the thing. So let's color this country with green, right? And since this country shares a border with the upper country, we cannot use green there. Let's use blue here. Now, since this color is blue, the country in the middle would be violet, right? Now, since that is violet, we want to minimize the colors. So, can we use green? No, we cannot use green in these two countries, the lower. But we can use the blue over here. So, let's use the blue here. And we can use the violet here. We cannot use the green yet. Now, can we use the violet in the lower country? No, we cannot use that there. We have to use the green here, right? We'll use the green here. But the topmost country cannot, we cannot use the blue or the violet or the green. So we have to introduce the fourth color here, right? So based on the color, let's write down the numbering here. Green will number that as 1, blue will number them as, let's say, 2, and the violet, let's number them as 3, and the red, let's number them as 4, right? So you see the chromatic number of this particular graph is equal to 4, right? So this is an interesting theorem, right? Okay. Looks like there is a chat message that has come. Okay, nothing that can be read out in the class right now. Okay. So yeah, so the maximum number is 4, right? So we cannot do it below 4, and more than 4 also we can use, but we do not want to use so many colors. And 4 is less than 5, so the graph coloring, the 4 color or the 5 color algorithm is valid over here. The theorems are valid over here. Okay. So some more problems are there on the 4 color and the 5 color theorems. We will revisit them later, right? Okay. So till now we have understood what is a chromatic number. We have uh, we have seen the definition of a planar graph. Planar graph is a graph that can be drawn only on a plane surface without the intersection of edges here and there, right? And then we would be uh, using the planar graph to understand the 4 color and the 5 color problem or the theorem. The 5 color theorem is a little easier theorem, right? There is a less restriction. We are allowing at most 5 colors in the 5 color theorem, whereas in the 4 color theorem we were allowing at most 4, right? So at most 4 colors in 4 color theorem and at most 5 colors in the 5 color theorem. Okay. Now, before moving on to the algorithm at the last, right, the greedy coloring algorithm, I would want to cover. I would want us to talk about matchings and coverings, right? So that we get a little idea about how to deal with um, how to deal with identifying different kinds of graphs, right? Okay. Now, yeah. So a matching. Let's try to write down the definition of matching. Definition of matching, and then we are going to talk about two types of matchings, right? So the definition of matching says as follows: the matching is of a set of edges, right, such that such that no two edges no two edges share a common vertex, right? Okay. Now, if it is not that obvious to you, let's try to get to an example. Now, our favorite example is that square graph, right? I'll use the blue pen for this. So the square graph, we can use the square graph over here. So the square graph is looks like this, right? And let's name the vertices as A, B, C, and D, right? Let's name our vertices as A, B, C, and D. And uh, okay, so here let's try to find out a set of edges such that no two edges share a common vertex. So you see the edge AB, right? And these are the edges that we are naming. Okay, the edges AB and CD form a matching. Very carefully, please have a note here. Why is this a matching? The vertices of AB are A and B, correct? And the vertices of CD are C and D. We said in the definition, what did we say in the definition? In the definition, we said that no two vertices, no edges share a common vertex, right? Which means that the vertices of AB, which are A and B, and the vertices of CD are C and D, there is nothing common here. No common. Therefore, the edges AB and CD form a matching. Now there can be multiple matchings. Alright. Now let's try to identify one more matching. AD and BC. Right? This is also a matching. Why is this a matching? Because the vertices of A and D, the vertices of A and D are A, D. The vertices of BC are B and C. And it is very easy to see that there is no common edges, no common vertices between these two. No common vertex. Right? So we can have a few more examples as well, but I think we all understand this very well. So in a matching, we can understand that we understand that if the edges are identified, so in this matching the edges are identified in such a way that the vertices are not overlapping. There are no common vertices. Okay. All right. Now let's. So I was. We were planning to talk about two kinds of matchings, right? One kind of matching is called the bipartite matching, right? Another kind of matching is called the um, perfect matching. The maximum matching and perfect matching. My bad. So what was the color I was using here? Black. Okay, let's use black here again. So first type of okay, I'll use this particular symbol. Yeah. The first type of matching is called the maximum matching. Maximum matching. In maximum matching, what happens is this contains so this is a matching with largest number of edges, largest possible number of edges. And there is another kind of matching called the perfect matching. In this kind of matching, we will be having, like every vertex is covered exactly once. There could be some matching in which the vertex is repeated, right? But there is no common vertex between these matchings, right? So that is there. But it could be possible that the vertex is, the some vertex is left over as well. That is also possible. So let's look at one examples at least of these two matchings, kind of matching, right? Um, okay, so in this example itself, right? Um, we have seen that. Let's look at the green example, right? The green example. In this green example, right? AD and BC is a matching. Now let's recognize the fact that no more edges can be added here, because the moment we add one more edge, let's say if we add BD, right? BD, if we add BD, then B and D are already covered, right? So this B and D would be, the vertex would be common. B is already covered here, D is already covered here. So these two vertices will become common vertices. So we cannot add any more edges here, and therefore AD and BC form a form is a maximum matching. All right. Apart from that, let's see whether this is a perfect matching or not. We saw the definition of perfect matching. In perfect matching, every vertex is covered exactly once, right? So let's see. In this particular matching, you see that A is covered once, right? A is covered once, B is covered once, C is covered once, and D is covered once. So our matching here covers all vertices. So AD and BC, both of these form a perfect matching. Right. So in this example was a pretty, what do I say? Uh, Easy kind of a thing, example, right? So yeah, it was pretty easy, right? Quite convenient example in which our matching turned out to be a maximum matching as well as a perfect matching. Okay. Now there was another topic. Let's see what was the other topic. We had the topic called coverings, right? So we have covered what is the definition of coloring, what is a chromatic number, what are matchings. We have covered to a certain extent the 4-color problem and the 5-color problem, and we have got covering here. Okay. Now the cover problem is the definition of covering, and how to identify whether a certain set is a cover or not is a very interesting concept. So let me try to draw a line here, right? How do I draw a line here? Yeah. Okay. Now coverings, right? So this topic is covering. So there are two types of coverings. One type is called the vertex cover. These are again very, very important concepts in computer science and computer application. Another one is the edge cover. there, like for example, you are planning to design and design a robot, right? And the robot is kind of driven by Internet of Things, by IoT. And so what does IoT do? IoT picks up information, like very less small kind of sensory information from the surroundings, processes itself in its onboard processing board, and takes action based on what kind of programming has been put on it, right? Okay. So the vertex cover and edge cover has to be calculated, like inside the Arduino or whatever language you are using, whatever chip you are using there, right? You have to configure that system in such a way that uh, the 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 IoT device, the robot, calculates the edge cover or the vertex cover based on what task that robot has to do, and find the optimal path, right? So for finding out, like let's say, the maximum profit or the minimum energy consumption, the vertex cover and the edge cover play a huge role. One such example is when we were talking about the traveling salesman problem today, earlier in the previous lecture, in the offline lecture, right? So we had seen that it's a minimization problem, right? So we have a weighted graph, and based on whether the salesman has to, the problem was the salesman had to start from Bangalore and end at Bangalore, and go to New York City, Mumbai, and Delhi and sell the products. So we were finding out the minimum path possible. Similarly, we were similarly, what we do here is we would be wanting to find out the vertex cover and the edge cover, um, and the IoT machine that I was talking about, and that would help us in optimizing certain things. Okay, so the vertex cover is a set of vertices. Okay, first of all, this is a set of vertices. Now there's a special condition here, set of vertices, such that all edges, right? So every edge of the graph, all edges of the graph are incident incident to at least one of these vertices. Okay, so this is the definition of vertex cover. We will look into the definition of the edge cover, and then we'll look into example, right? So edge cover is a set of edges, and such that uh, every vertex is incident to at least one of these edges, to at least one of these edges. So you see, there is a terminology. So the terminology here, right? There is a terminology called at least, right? This word at least here. There is another term here called at least. So these are the terminologies, seeing which you should be able to, at a master's stage, understand that we are actually optimizing the problem, right? We are either trying to find out the maximum or the minimum. Your choice, gentlemen. Please go ahead. Okay. So what we do is that, uh, yeah. So what we do is that, let's look at an example, and we will. Anyways, I think people are losing a little bit of focus, but we'll look into an example and we'll close. I think that would be better, right? Um, uh, are you? I would definitely recommend you to go. uh, okay, so um, okay, I think I could make some changes here. Okay, anyways, um, okay, so let us try to look at an example and then we will wrap up, right? Okay. So an example here would be, let us go back to our original problem there, right? Um, our famous example of four uh, vertices A, B, C, and D, and they're connected by these four um, they're connected by these four edges, right? So you see here, if we choose, so what is the definition here? We want a vertex cover, right? We want vertex cover. We want to look at the vertex cover. What is a vertex cover? Vertex cover is a set of vertices such that all edges are incident to at least one of these vertices. So if we choose the vertex cover as A, B, C, D, right? Then, so the method is as follows, right? So we will choose a set of vertices. We may choose, we may want to choose A, B, C, D, or like we could very well choose, A, B, and D, or maybe if it is if we don't want so many vertices, maybe we could choose just A and B and C, right? Or maybe if it is fine with you, we could choose just A and C, right? So whatever we choose, let's first choose ABC maybe, or ABCD. ABC is better, right? What we do is that we write down all the edges. So this is E1, let's name this E2, let's name this E3, let's name this E4. So E1 is equal to AB, E2 is same as AD, and then E3 is same as BC, and E4 is same as CD, right? What are the what are the vertices here? The vertices are A and B. What are the vertices here? A and D. What are the vertices here? B and C. What are the vertices here? C and D, right? Okay. Now, what we have to do is we have to see that whether each of the vertices, right? So out of this A and B, whether one of them is there in this set, correct? So what we'll do is that from here we see that okay, A and B both are there in the vertex cover. Here A is there in the set that we have chosen. B and C both are there in the vertex cover set that we have chosen. From here, C is there in that set. So since all of these are true, therefore what we can say is that VC is a vertex cover. We'll go through this again. We'll go through this again. Okay. Now, let's try to let's try to bring this thing down here. Let's bring it down here again, right? Okay. Now let's assume like we don't need the graph anymore. Let's assume that our vertex cover is A and B, right? We'll check whether this is true or not. So A and B, right? So A and B both belong to the vertex cover. Here A belongs to the vertex cover. Here B belongs to the vertex cover. But here none of them, right? C and D do not belong to the vertex cover. And since there is at least one edge in whose vertices do not belong to the set, we will say that VC is not a vertex cover. Is this understandable by you guys? Can I have a thumbs up from you? This is a little complicated concept, but easy. Yeah, absolutely. Okay. Um, all right. Now let's see. Let's try to find out one more example here, right? Uh, where we are dragging on this example because uh, students find it a little bit difficult to understand this concept, right? Um, we'll look into this. We will, yeah, we'll do that. Harika, we'll look at one more example. So let's. So what is we want to design a set, right? A set, a set. We want to design a set of vertices, okay, such that for all for all edges, at least one of the vertices is in the set. What I mean here is either A or B should be there inside our set. Both can be there, not a problem. A or D should be there in our set. Either B or C should be there in our set. Either C or D can be there in our set. Now you would be wondering that, okay, what if we choose our set in such a way that what if we choose our set as follows? Let's choose our set VC as equal to A, B, C, and D. If this is done, definitely it is true because A and B belong to this set. Yes. A and D belong to this set. Yes. B and C belong to this set. Yes. C and D are also in this set. So VC is definitely a vertex cover. That is for sure. But we want a minimum vertex cover, right? We want a minimum vertex cover. So let's try to see if like A comma C is a vertex cover or not. Is vertex cover? Yes or no? So you see from E1, A is there in our new set, correct? It is there. From E2, from E2 as well, A is there, not a problem. From E3, C is there in our vertex cover set. Good. From E4, C is there again. Right? So this particular set VC is indeed a vertex cover. So I mean this particular content that we are creating right now will be uploaded. We'll share this video with you. You can go through this and convince yourself. So vertex cover set is a small set subset of the vertex set such that all the edges touch the vertices in this particular set. Okay, it's as if saying, roughly it says, one of the we can find some problems in which there are some airport hubs, right, or like some seaports which are like we send ships to most ports, right, or maybe junctions when there is a in a railway junction, right. Not all railway stations are junctions. Some stations are like you can just go on the left or to the right, correct. There are like left there are west and east cabins only, but there are certain railway stations which are junctions, right. So there can be like you can go to a completely different route. You can go to three different places from that particular city, right. So for example, from Bengaluru, SBC, right, from that particular railway station you can go to like Mysuru, you can go to Bangalore, you can go to Chennai, you can even go to Calcutta, right? Okay. But however, the cantonment railway station, that is, I guess, that's not a junction. On one side, you can go to, like it's a railway station on the railway track. It's kind of like that, right? So there is a railway track, right? And there is a city nearby, there is a town nearby, and there is a railway station over here. So we would be not interested in including this in the vertex set. We don't want this, do not want this in the vertex cover, right? However, we would definitely want a city. Let's say there is a city and there is a railway line from another city, there is another railway line from another city, there is another railway line going to another city. We would definitely want this particular, we want this is in the vertex cover. Anyway, it's a very interesting concept, and we are really running short of time. We would go through the edge cover and we would stop there, right? Okay. I would add a new page here and then we'll go to edge cover. Okay. Again, let us draw again our favorite graph, right? A B C D. In the questions, guys, we would be asking you whether a given subset is a vertex cover or not, and whether a given subset is an edge cover or not, right? So again, let's name this A, B, C, D. I think I'm naming them wrong, but anyways, doesn't matter. So here, the vertices, what are the vertices? The vertices are A, B, C, and D. So our aim, what is our aim? Our aim is to choose, we want to choose a set of edges. Oops. We want to choose a set of edges. All right. We want to choose a set of edges such that such that such that the edges cover all the vertices. All right. The edges should cover all the vertices. Um, so let's see, how we can go ahead here. So let us try to see whether um, AB and BC is an edge cover or not. Okay, EC means edge cover. This is an example. What we're doing here is edge cover. I think I should write it down here. Okay, edge cover. We are doing edge cover here. Okay, so we want to see if AB and BC is an edge cover or not. Now, let's see. We have got the vertices A, B, C, and D, correct? A, B, C, and D. A is covered here, very good. B is also covered here and here, very nice. C is covered here, very good. D is not covered anywhere. So, this implies that this is not edge cover. We'll look into multiple examples, don't worry. Okay, let's try one more, right? Let's try AB, BC, and CD. Is this an edge cover? Yes or no? Let's look at that. A, B, C, D. These are the four vertices. A is covered here. Very good. B is covered here. B is covered here as well. At least one is enough, but it is covered in two places. Very nice. C is covered here. C is covered here. Two places. One is enough, but two places. Well and good. D is covered here. Amazing. So this is an edge cover. This is edge cover, right? Okay, let's look at one more example. Again, if you choose all the edges, that is fine, but we want a minimum vertex cover. Sorry, a minimum edge cover. We want minimum vertex cover and minimum edge covers. You see, the IoT device wants the minimum edge cover and the minimum vertex cover. So we want to design, we want to know mathematically how to find out the minimum edge cover. Correct? So let us try this. Okay, let's use a different color pen, right? Okay, so let's try this. Let's try AB and CD, right? Is this an edge cover? Let's see whether this is an edge cover or not. How to find out whether this is an edge cover or not? We will write down A, B, C, D, all the vertices. A is covered. A is covered by AB. B is covered by B is covered by AB again. So till now A is covered, B is covered. Let's check whether C is covered. Yes, C is covered by, but C is covered by CD, right? Very good. D, well, D is also covered. D is covered by CD. Very nice. All the vertices of our graph are covered. Therefore, this particular set AB and CD is an edge cover. Okay, so we have all right. Can we have a thumbs up series of thumbs ups if you have understood? If you have not understood, then also you can tell me, right? I will be giving you one more example if it is possible. I'm sure it is possible. Okay, thank you. I can see everyone. Sundar, I can see Nayana, Tasim, I can see Manish, I can see Archana, Guru Kiran. Great. Purnankit, fantastic. Divya has also, Shweta has sent. Thank you. Good. Sri Vidya. Amazing. So this, more or less, this covers a major chunk of this module, right? What we'll do in the next lecture is let's go back and check how much has been done, right? We'll do the greedy coloring algorithm later, right? So we have covered till now coloring, chromatic number, matchings, coverings. Some part of we have understood the problem, like the 4 color problem and the 5 color problem. The greedy coloring algorithm and the chromatic polynomial will be done later. Okay, are there any questions right now? If there are not, we can end it up. In the chat box, how many questions will be there for this topic and 4 color topics, sir? Well, again, you see, modules 3, 4, and 5 are there in your test, right? So, the division of problems. So there will be ABC, ABC 6 there, and ABC, ABC 6, 6, 12 questions. 12 questions from 3 modules. So on an average, 4 questions from each module. So out of those 4 questions, it will be like, uh, 2 versus 2, right? So uh, what I mean to say, it would be either 1A, 1B, and 2A, 2B, something like that from each module. 1A, 1B, 2A, 2B from one module, and then 1C, uh, 3A from one module, and 4C, sorry, 2C, 4A from another module, and from the third module it would be 3B, 3C, 4B, 4C. So like that way we'll be creating the question. Yeah, what I'll do is that I'll go to the last page here, and in the last page maybe um, a rough idea about how the question paper would look like, right? So this is module 2. This is module, not module 2, my bad. Module 2 is done already. Okay, so module 3, module 4, module 5, right? This is a rough idea, okay? To please be ready for surprises. 1A, 1B, or 2A, 2B. 1C, 3A, or 2C, 4A. 3B, 3C, or 4B, 4C. So this would be kind of the question paper pattern. Um, yes, I do have a YouTube channel. Please do subscribe to my channel. I think if there are 50, 60 more subscribers to my channel, it would be great. There are not much topics relevant to your uh, syllabus that are there till now, but later, I'll definitely try to upload some videos. um, yeah, they are mostly so what I'll do is that I'll upload these channels, this video to the channel. Actually, the video is still rolling, right? It is more than 1 hour. So, so please do speed up and watch and go back and forth, like the video, share the video, and so on. All the stuff is there. Uh, okay, and there is a common question asked by students about what are the common questions, what are the important questions. I would definitely suggest you to go through this, like this document. I'll share this document definitely in your forums, right? Namely the WhatsApp groups. Um, so please go through this. Please try to recall. Please discuss with your friends. Ask doubts. But at the same time, there will be some questions which, like Professor Shabana and myself, we will have a discussion and see what kind of problems we can share with you. Right? Okay. See you in the next lecture, guys. Can we have final emojis? Okay, Manish, Tasin, Muhammad Tasin. Hope your Ramadan is going on good. Okay. Yes. So everyone, please do give these emojis. I'll take a screenshot. Right? A screenshot is important. Okay. Some more, guys. Some more. Yes, that's it. No, some more. Not the thinking emojis. Come on. Give better emojis. Yes, that's right. That's better. Great. Thank you so much. We will meet again in the next lecture and we'll go ahead and yeah. Okay, I will end this meeting from, I will end the recording from here first. Thank you for watching.